All right, everybody, Math 150, we're on a roll today with section 3.1. We're now going on to learning objective number 2, and that's graphing polynomials using transformations. So the idea of transformations is that we know a basic graph, and we alter it a little bit, but we can predict how those alterations are going to move the graph along on the XY axis. So here are some polynomials that you guys should know based on some stuff we've talked about in our library of functions. You guys should know that if we have a degree 0 polynomial, that just means it's f of x equals a number. F of x equals 5, f of x equals -3. That is a constant function, and it is going to be a horizontal line every single time, okay? So if you see something like this, here's an example of a degree 0. If you see f of x equals, let's just say 7, the way that graph will look is it's going to have an output that is always 7. So what that means is for every input, the output will be exactly the same. It will never change. It will always be 7. So what's going to happen is we're going to have an y-intercept of 7, and this graph is just going to go straight across like this and make a horizontal line. So there is the graph of the constant function. If the number were different, the horizontal line would just move to that location on the y-axis. In the second one, we have a degree 1 polynomial, and in this degree 1 polynomial, this is just another way to write mx plus b. You guys are all familiar with mx plus b. A1 is the coefficient of the x, that's your m. A0 is the number by itself, that's your b. So it's just another way to write mx plus b. We know that in this case, what's going to happen is we're going to have a graph that has some kind of slope associated with it. If A1 is positive, if the slope is positive, the line will be going in an increasing fashion. If A1 or M is negative, we'll have a decreasing line. So this is what your degree 1 polynomial is going to look like. And then your degree 2 polynomial, again, we recognize this, I hope, as our parabola. It's our quadratic. It's just that we write it as a quadratic in previous sections. We wrote it as ax squared plus bx plus c. We're just using the polynomial notation for the coefficients. So that's where the A2, A1, and A0 come from. We know that this function is going to be a parabola. We know that for our parabolas, if the leading coefficient is positive, it will open upward like this. And that will be, oh, I'm sorry, put it through the origin there because that's the basic one. That's if A2 is greater than 0. And if A1 is, I'm sorry, if A2 is less than 0, then we would have a parabola that would open downward like this. And that's if A2 is less than 0. So those are our basic first 3 polynomials you should all be familiar with. If you see a degree 0, horizontal line. If you see a degree 1, a slope line. And if you see a degree 2, it's going to be some kind of parabola. This is going to help us do our transformations. The next thing we have to talk about is the idea of a power function. Now, this notation should look familiar to you. It's the same exact notation we had for the polynomial, but the polynomial continued with a sub n minus 1, x to the n minus 1, because the next term dropped the exponent by 1, the next term dropped the exponent by 2, and then we would continue all the way down to when we finally wore that exponent down to 2, and then wore the exponent down to 1, and then when we wrote the exponent down to 0, so we had a 1. So this looks like the beginning of the polynomial. And that's because that's exactly what it is, okay? The power function is when you ignore the rest of the terms and just look at the first one. So when the power function is concerned, you're just looking at that leading coefficient and the x that goes with it. The reason you want to be familiar with your power functions is because all degree, for instance, 5 equations or graphs will look somewhat similar. All degree 6 will look somewhat similar. So this is the term that we get the degree from. We know the degree by looking at this particular term. So that's the reason that power functions are kind of important. The degree really sets the stage for what this graph is going to look like. So let's take a look at some of these power functions graphs, okay? So here are the basic graphs of all the power functions degree 1 through degree 6. So in this one, we're talking about the graph of y equals, I just kept it at 1, so this is just going to be x to the first. This next one is going to be y equals x squared. This next one is going to be y equals x cubed, and right on down the line. So we're going to get x to the 4th here, x to the 5th here, oops, and x to the 6th as our last one. So there's x to the 5th, and here's x to the 6th. Now, if you put a coefficient in front of any of these, if the coefficient were negative, it would actually flip the graph, okay? So if you were asked about what does y equals negative x squared look like? And we just kind of talked about that. All it's going to do is flip the graph over. That's what the negatives will do. The positives give you the red graphs I'm showing you. The negatives will give you the flip over the x-axis of this. The other thing that could happen is what would happen if you did a number in front of the x. So over here, let's say I did the following. Let's say on this graph, I did, let's do this one. Let's say over here I did y equals 5x. Well, you guys know that that would make your line steeper. So I'd actually get a very similar graph. It's just that it would be much, much steeper. That's what coefficients do to all these graphs. If I were to do a number in front of, for instance, the x to the fourth, if I made this 10x to the fourth, this graph is still going to go through 0, 0, but it's just going to be much, much steeper. It's going to go up much, much steeper than what you see. So coefficients greater than 1 make it steeper. Coefficients less than 1 actually flatten it out. And what I mean by that, if you had y equals 1/10 x to the fifth, again, you still go through 0, 0. That origin's always going to be hit, but you would have a much flatter graph. It would flatten this graph out a little bit. So it wouldn't be as steep. It would flatten it out a little bit. So again, coefficients greater than 1 in the power function make you steeper. Coefficients less than 1 in the power function make you flatter. Okay, so we'll come back up here. We're just going to write that. So for any power function, if a sub n is greater than 1, that will make the basic graph steeper. And if a sub n is less than 1, that is going to take your basic graph and it's going to make it flatter. It's going to flatten out your basic graph. So for this one, it will be flatter. All right. So another thing to keep in mind about the power function when we come back down here. All right. And I'm going to just go back to the original ones. I'm going to go back to the original power functions in each of these cases. I want you to notice the pattern that's developing as we look at these, okay? When you look at these functions, all of them, for each one here, I should have written this down, all of these, a sub n is greater than 1 for all of these, okay? I'm sorry, a sub n is greater than 0 because they're positive. There's a pattern. You kind of see a pattern going on. What I mean by that is in the degree 1, you have a down, up going on. In the degree 2, you have an up, up going on, but degree 3 turns to down, up. Degree 4 is up and up. Degree 5, down, up. Degree 6, up, up. I would bet you could all figure out that degree 7 is going to follow this pattern of a down, up. Degree 8 is going to be an up, up. So it sounds kind of silly saying down, up, up, up. What are we actually talking about? We're talking about something called end behavior. And end behavior is asking, what does the graph do? What does the graph do on the far left and on the far right? So in the beginning, we're going to say the far left and the far right. It really has nothing to do with the interior of the graph, the middle. It's all the way on the left and all the way on the right. So when we say all the way on the far left and the far right, there's a way to translate that. The far left, what that implies is that the x values are on the far left. They're big, big, big negative numbers. It implies that x is going to negative infinity. And on the far right, what we're saying is that x is going to positive infinity. Okay, so now as we look at these three, you can see right now, let's look at the degree 4. For the degree 4, as x goes to infinity, we're going up. Well, up and down are the y values. So we're going to say that y is going to infinity. And I apologize. That is actually as we go to negative infinity. So let me just fix that. I apologize for that. That's right as we go to negative infinity. We're going on the left side. Y is going to infinity. Over here, x is going to the right. So x is going to infinity. But the y is also going up. So y is going to infinity. Okay, so on both sides, you're going up. So y is going to infinity. On this next one, X is going to the far left, it's going to negative infinity. As this thing moves to the left, you can see it's going down as it moves to the left. So that means that Y is going to negative infinity. And when we look on the other side, X is going to positive infinity because we're going to the right. But what's the Y doing as X goes to the right? Y is going up. So Y is going to positive infinity. So we've got this idea of end behavior, trying to figure out what the graphs are doing on the ends. Here is the pattern that you need to know for odd degree. As X goes to negative infinity, Y goes to negative infinity. And as X goes to positive infinity, Y goes to positive infinity. So that's what's happening for an odd degree. And again, that is if our leading coefficient is greater than 0. For an even degree, as we are all the way on the left, in other words, as X goes to negative infinity, Y is going to positive infinity. And when we move all the way to the right, that's like saying when X goes to positive infinity, Y is also going to positive infinity. And again, that's when your leading coefficient is greater than 0. So you can actually make a really quick prediction about what any graph would look like, because all graphs kind of follow the pattern of their power function. And that's when you get rid of all the other terms. So one more thing to think about on this one, just to give you just kind of another example to really solidify all of this. What I'm saying here is, if you're given this graph right here, f of x equals 7x to the fifth minus 2x to the fourth plus 3x squared minus 1/2 x plus 10. And I ask, give me a general idea, a rough idea of what that looks like. All you've got to do is say, well, let's look at the first leading coefficient. That orange piece right there, 7x to the fifth, is the power function in this one. And I know that because this is a degree 5, that as we go all the way to the left, the y values are going to go all the way up. And as we go all the way down. Okay, because that one's odd. It's an odd function, odd degree. So that's going to go all the way down. And we also know as x goes all the way to the right, the y values are going to go all the way up. So for odd functions, you're always going to get this. So this graph right here, it's not going to be exact, but we're going to know the end behavior for it. We're going to know that when we draw this thing, it's going to come from this direction down here. It's going to start, I say that's starting down. It's going to start down. And it's going to end in this direction up here. It's going to end up. So I know my graph is going to have this kind of shape to it and this kind of shape to it. What I don't know is what's going to happen in the interior in here. I don't really know what the graph's going to do. Power functions are nice and smooth. We know that a power function would just kind of continue and just kind of go through the origin and do this, all right? But this function has all of these other terms in it. And what these terms are going to do is they're going to create some bumps and some bruises and some ups and some downs. So we're not really sure what's going to happen. But we do know that even if it did the following, even if it did something like this, even if we saw a lot of kind of turns and changes, so let's say it just kind of, maybe it does something like this. Maybe it goes up and down and up and down and comes back down and goes back up. It's still following kind of the same basic idea, especially when we think about the end behavior, especially of our graph, our power function, that would look like this one, okay? So again, not exact, but it's still following the basic idea of a graph that looks like this. So that's the idea behind the power function. It lets you kind of visualize what the graph looks like, albeit roughly. It still gives you a chance to give you an idea of the graph. We are going to look at 2 examples to wrap up today. We're going to graph these 2 polynomials using transformations. Yesterday, when we were talking about absolute value, one of the things I told you is look at that 0. Find where that 0 is. Let the 0 help you with the transformation. So we know that all these polynomials have a point at 0, 0. Well, when we look over here, we see 2 shifts. We see the x being shifted and the outside being shifted. Now remember, the inside shift works the reverse the way you would think. You would think -5 would move it left. -5 in this case moves it right, moves 5 units right. So that means that 0 is going to shift over by 5 units, and it's going to end up right here at 5. And again, it's because I need to plug 5 into this to get out 0. So I'm finding out where the 0 is. It's going to shift over 5. So now, what does the plus 4 do? Well, the plus 4 is outside the parentheses, so that's going to shift it down. This does it the way you think. It's a minus 4. It's going to be a shift down 4. So I'm going to go 5 to the right, and I'm going to go down 4, and I'm going to relocate my new point right there. So this guy's going to go over 5 to the right, and now it's going to go down 4. I am now going to take that shape, and I am just going to redraw it right here. Okay, and that's what the shape's going to look like. So that is how this transformation works. Very similar to the absolute value transformations we talked about yesterday. We're going to look at one more before we end. On this one, this guy here, I've got a little typo. I'm going to fix this. This guy here should not be a 3. That should be a 4. Okay, so we're going to take this x to the 4th shape, and we're going to translate it. But this one has kind of a tricky part to it. It's got this negative here. Here's how I advise you to handle the negatives. I like to factor the negatives out. So what I want to do is I just want to take the negative out, and that's going to make this x plus 8 raised to the 4th minus 3. And when I multiply that back in, you're going to see that this piece becomes negative the way we need it to, and this piece becomes positive the way we need it to. The reason I want to do that is because I want to get my transformations based on if the leading coefficient or the positive factor is in front. So I'm taking out the negative. Now, to me, I can shift x plus 8 to the 4th minus 3 really easily, okay? Because this is going to have a shift on the inside. So we're going to move this now. Again, plus 8 might make you think, great, on the inside, it's the reverse. We're going to move 8 to the left. And then this guy right here is going to be the up and down translation. This is going to move 3, and this one works the way you want. This one moves 3 down. So that means my 0, 0 is going to move 8 to the left. So it's going to go this way 8, and then it's going to move 3 down. So it's going to move 3 down. That's going to take us down here to negative 3. So this point is going to be here now at negative 8, negative 3. I would now draw this shape right here, and that's what I would get. But remember, we had a negative. So really what we've got to do with this shape is we've actually got to flip it. So that shape is going to get flipped. So when I go to draw this on my graph over here, I'm going down 3. I'm going over negative 8 in this direction. I'm putting my 0 down here. And now that shape is going to end up like this. So the bottom line on this one, the shift inside the parentheses works the reverse of the way you think it should. If it's a plus 8, it actually goes to the left. The shift outside the parentheses works the way you want it to. If it's a plus 3, you're going to go up, okay? And if there's no negative in front of the x factor, then do it the way it looks. Don't worry about it. Just shift it the way we said. If there's a negative in front, I strongly encourage you to factor out the negative and think of it as doing it without the negative first, and then the negative is what flips it over. I hope that makes a lot of sense to you guys. I'll be back with another video shortly. Good luck with your homework today, and I'll talk to you soon.